Right, so very good morning to everyone. Sorry for the technical difficulties. I think there's some technical issues. So first of all, I would like to welcome everyone to this webinar event. So my name is Kanendra, and thank you for joining us for the IEEE PES Malaysia Research Discourse webinar session. This is our third session out of all 4 sessions. And in this research, I would like to introduce our speakers for this session. So our first speaker for today is Associate Professor Dr. Muhammad Rafi Azman. He's born in Selangor, Malaysia in 1976. He received his MSc degree in Power System and High Voltage Engineering from the University of Technology Helsinki, Finland in 2006, and doctoral degree in Technology from Aalto University, Finland in 2014. In 2001, he was project engineer with Foxborough, Malaysia. Later, he joined Power Cable Malaysia as an electronic engineer until 2004. He served with the School of Electrical System Engineering, UNIMED, University of Malaysia Perlis, since 2004 until now. His current research interests include renewable energy, power system distribution automation, fault localization, power quality, and artificial intelligence application in power system. He's a member of IEEE PES, the International Association of Engineers, and the Board of Engineers Malaysia. So today, Dr. Rafi will deliver a presentation on his research area titled, A Novel Wide Area Fault Detection and Location Using Sequence Values and Enhanced Two-Terminal Impedance-Based Method. So I would like to welcome Dr. Rafi. The floor is yours. Thank you.
Okay, thank you, Dr. Nindra. Okay, Assalamualaikum and good morning to everyone. Thanks to IEEE PES for this webinar. Today, I'm going to share the session about novel wide area fault detection and location using sequence values and enhanced two-terminal impedance-based method. The presentation today is about the result from the RGS project that I've received for. It is part of the power system and optimization group research work. Okay, a bit about me, those who are joined. My full name is Muhammad Rafi bin Azman. I born in Selangor. I got my master's degree from Helsinki University of Technology in Finland. Then my PhD also from Finland in Aalto University. Before joining UNIMED, I was a project engineer with Foxborough and also from Power Cable Malaysia. Okay, a little bit about UNIMED. So UNIMED before this, known as COCOM, started in 2001, and the first intake is about 116. Then nowadays we have more than 5,000 student intake. So if you go to Perlis, UNIMED, we can see that UNIMED campus is distributed all inside Perlis. We have one campus close to the border Thailand. We call it Unicity Sungai Cucu campus, and also one in Kanga City, where we have a business and media, new media program there. And I work in main campus in Pau Putra. So introduction to fault in power system. Okay, the reliability and the security of the electric power supply can be affected by the faults that occur in power system. The transmission line are important parts of the electrical network, and we need to be installed across a long distance and causing transmission line vulnerable to all kind of faults. Okay, when fault occurs, we need to locate the fault immediately in order to do repair works and to resynchronize back into the network. And faults may be due to the lightning, a tree, crane touching a lifeline, polluted insulators, human error, and aging of the equipment. Due to the complicated weather and field condition, it is sometimes difficult to patrol the lines, and thus it is vital to employ equipment that can locate the faults with the accuracy of 1 tower, for example. Here is some example of the data statistic that we found in the literatures. And we can see that most of the faults in transmission or headline is one phase fault, like phase to phase or phase to ground. And we can see that the unsymmetrical fault is a fault that dominant in the transmission line. And the figure in the middle, we can see that the percentage of the transient fault is higher than the permanent faults. And at this right side, it is the one of the figures from the grid distribution statistic in Norwegian countries. In this figure, we can see that, for example, in Denmark, the natural causes is the most highest disturbance happen in the transmission grid. And while for the country like Norway, the technical issue is the most highest grid disturbance. So why we need fault locations? So first we want to reduce the cost with the out of order condition of the transmission line. And also we want to do the monitoring for the faults for any natural events such as wind, storm, heavy snow, icing, wind, light, and also the lightning. And we want to locate the fault with the high precision so that can be easy for the workers to do the corrections. And also the distinguishing between the random faults caused by the lightning or fire under the lines and predictable discharge due to the contaminated insulator, swaying or growing tree. And we need a fault location for finding and correcting the trouble spot on a regular basis to avoid other discharge for repeat faults and to improve the reliability. So the fault location method basically can be classified based on the numbers of measurement used as the inputs. And here we have a figure here, we have the example for one terminal methods. So it is the earliest fault location method. So use a measurement from the local terminal here. Okay. And this kind of fault location method is less accuracy compared to the others. So because we need the many parameters, unknown parameters to do the estimations. Next, we have the two terminal method. These two terminal methods. So the measurement has been done for these two terminal, and these two terminal can be communicated through fiber optic, for example. And it has the highest accuracy among all fault location methods, and the measurement can be synchronized or unsynchronized. And nowadays we have the latest method known as wide area methods. So we use the wide area measurements for the limited number of phasor measurement units, or known as PMU, or from the synchro phasor in the networks. So all these PMU or IEDs will gather the information or the signal and will transfer it to the central locations. Okay. Then the measurement can be synchronized using a GPS. And regarding the fault location technique, we can assume that there are two main fault location techniques that has been used in the power system network. So here, the number one is, we call it impedance based. It measures the apparent impedance from the fault points to the local points measurements here. And we require the line impedance parameter in order to do this algorithm. Second method, known as a traveling wave or TW, the traveling time will taken by the fault wave is used to estimate the fault locations. And this method require high sampling device in order to read the fast traveling wave. Other method beside these two methods, we can use state estimation, support vector machine, neural network, and other artificial intelligence technique to locate the faults in the line. Okay, most of the literatures assume that the line as a lamp parameter without considering the effect of the hybrid circuit. It is a hybrid circuit, a combination of several types of line having different kind of electrical parameters. Here is the hybrid example of hybrid circuit. So we have a line parameter which are not uniformly distributed along the lines. And this non-uniformity will make the current at the sending end and the receiving end will not be phased to each other. Another one issue is regarding the charging currents. The charging current exists due to the distributed shunt capacitance of the circuit. So it exists during normal and also fault conditions. And the charging current strength depends on the voltage and the capacitance of the frequency. So for the long line lengths, the charging current will be much higher compared to the short one. And when we use the cable, it will give more charging currents. And according to the IEEE guides, it will produce error in the line protection relay and fault location estimation. What area measurement system or WAMS was introduced due to the advancement of the phasor measurement technology, whether it as a standalone device or as a built-in feature inside the IEDs or relay like this one, okay? So this example, the line protection relay with synchro phasor measurement inside it. And also this is the standalone device, PMU. And this application used normally for control, monitoring, and protection examples. So here is the example of the architectures of the WAMS. So we can see that there are few PMU, also maybe others relays. Inside it, we have a synchro phasor measurements. So from these equipments, all the data or information signal that gather from this equipment will be sent directly to the cloud. So for example, we have a 3 phasor data concentrator here and will be sent to this cloud, and the cloud will send all the information to the data center. And from the data center, the other application can be used the data in order to find, for example, port locations or to do some monitoring and also the protections. Okay, in this work, we have identified 3 main problem statements. First, regarding the PMU placement. Second, we have due to the hybrid circuit that I discussed before. And the third one also I've discussed before is about the charging current. Regarding the PMU placement, for the conventional fault location methods, it requires the measurement from all line terminals. And normally the measurement are not centralized and synchronized. And based on our findings, we found that none of the PMU placement for faulted line identification and fault location were considered with the effect of the generator in-feed currents. Here, in this work, we have 3 main research objectives. The first one is to develop an optimal PMU placement strategy based on the limited number of PMU. And the second is to develop a wide area fault detection and location algorithm which can detect and locate the fault accurately on homogeneous and also for hybrid circuit. And the third one is to develop a wide area fault location algorithm by taking into account the effect of the charging current. The research scope of this project includes a type of transmission network that we use. For this work, we select a IEEE 5 and 39 bus, and also the PMU placement strategy, the measurements, the software that we're going to use. We use ATB Draw and also the MATLAB Simulink, the method that we apply, and also other considerations like charging currents, hybrid circuit, and also the connected loads. Okay, in this work, before we use the fault detection and location algorithm, the PMU placement strategy need to be applied, and the PMU placement strategy is based on the 5 rules. For the rule number 1, the bus voltage were calculated using the voltage from the adjacent buses, while the line current were taken from the adjacent buses were installed PMU. If not installed, it will be calculated using the KCL. So in this figure, we have two figures. For example, bus with only two connected lines. So here is the example for two connected lines, and here if the bus with only one connected line. Okay, the buses that comply to this rule were removed from the next rule. So rule number 2, we have generator buses as a PMU buses. So in this bus, we have a generator where the input current through this bus. And for why we need the PMU buses, because there will be an input current from the generator directly to the bus. If we did not count it as a PMU bus, then input current from the generator that is unknown will affect and the influence, and it will influence the accuracy of the fault detection and also for locations. Next, in rule 3, the remaining buses that have at least one line connected to the PMU bus at the remote end will not be selected as a PMU bus. Okay, for example, here, bus number 26 will not be installed with the PMU. And next, we have rule number 4. For this rule, PMU will be installed at remaining buses which will produce a high number of buses with at least one line connected to the PMU. Okay. For example, here, bus number 4 will be selected as PMU bus because it will make bus 14 here has at least one line connected to PMU bus at a remote end. So bus number 14, not a PMU bus and previously not connected to any PMU bus at the remote end. And the final rule is rule number 5. PMU will be installed at the remaining buses after rule number 4. For example, here bus 8 will be selected as a PMU bus. This bus previously not a PMU bus and do not have at least one line connected to PMU bus at a remote end. So for this is the PMU placement flow chart. So it will start with the rule number 1 and then goes to rule number 2 that I've discussed before, and we will record the PMU bus here, and then we'll go through the rule number 3 and again rule number 4, and finally we will record the PMU buses up to rule number 5. Okay, here is the result for 5 bus and 39 bus. So for the dotted blue circle is the location of the PMU. For example, for network 5 bus network, based on the PMU placement strategy, we found that we need 2 PMU for all these buses. So the 2 buses located at bus number 1 and bus number 2. While for 39 buses, based on the PMU placement strategy, we have found that we need to use 12 buses for these 39 buses. So this is the PMU that located at the bus. Here is the example of the measurement source for 4 lines in 39 bus network. So for example, here the circle refer to the PMU bus. For line, for example, line 2 to 225, local at bus 2, remote at bus 25. These 2 buses is a PMU bus. And so the measurement were taken directly from the PMU, okay, for voltage and for the currents. For example, here both of these are not a PMU bus. Then the calculation for voltage and current will be done by using KVL and also the KCL method. Okay. And you can see for this one, we have one doesn't have PMU and one bus have a PMU. So those who are buses have PMU will measure the voltage and current signal directly using the PMU, while for the non-PMU buses, we will use KVL and also KCL technique. Okay, for first fault detection method, for the first method, we'll use the comparison of total current between fault and pre-fault conditions. So it will be used for all lines in the networks. And in this method, we use positive sequence value as the inputs. Okay, for example, here in this figure, we have a local and remotes, and we have the local current pre-faults. For example, we have a fault happen here, and for the faulted line, for example, here we have a I fault which is higher than uh, local current pre-fault plus remote current pre-faults. Okay, so this I fault can be calculated using the positive sequence versions. Here it's the equations, and for the we compare for the unfaulted fault. Okay, unfaulted fault lines, the positive sequence currents is equal to positive sequence current pre-faults plus at the local and also the pre-fault positive sequence remote currents. And for the second method, we use bus voltage checking. We use negative sequence values, and use only for line with a share measurement source with the other lines, and to determine the actual faulted line from the several possible faulted lines. And this method is in conjunction with the first fault detection methods. In this method, the bus voltage checking is used for a common bus with two connected lines, and also for the common bus with more than two connected lines. So when a fault occurs at any point in line 1, 2, the negative sequence bus voltage of bus 2 measured from bus 1 will be less than the bus voltage measured in the same from the same bus. Okay, so for example, here we have a 3 bus here. So bus 1, 2, and 3. So when fault occur at any point in line 1, 2, point X, we can measure the bus voltage at bus 2 using the negative sequence current measured from bus 3, which is less than the negative sequence voltage bus voltage number 2 measured from bus number 1. So this negative sequence bus voltage can be calculated using this equation. Okay, the same principle apply for faults that occur in point Y. Okay, point Y. So we can use this equation in order to compare between the measurement from 1 and also from bus 3. Okay. Okay, for bus voltage checking for common bus with more than two connected lines. So here is the example of a common bus with more than two connected lines. So here we have a bus 1, bus 2, and other connected lines. So when fault happen at this line, for example, at line X, the negative sequence bus voltage current for negative sequence bus voltage measured bus voltage number 2 measured from 3 is equal to negative sequence bus voltage number 2 measured from 4, and is equal also to the negative sequence bus voltage 2 measured from 5. Okay, so this negative sequence bus voltage can be calculated using these equations. And the same principle can be applied for the faults at line 23, 24, and also line other lines. Okay, for example, line 25. Okay, for fault location method, to develop it is based on the two terminal methods. So it enhanced by using KCL and KVL to obtain the current and voltage for terminal which do not have any PMU. And in this algorithm, we use negative sequence value as the inputs. So based on these figures, we can develop the algorithms and we can implement it into the negative sequence. Okay, so this is the formula that we use in order to calculate the fault distance or estimate the fault distance using negative sequence values. Okay, regarding the fault distance and fault location for hybrid circuit, in this method, we separate the hybrid circuit into two sections. Okay, so for example, in one line, we have two kind of cable lines. One is based on overhead lines, maybe bay conductors, and one is using the cables. Okay, so this is the point of connection that we set as a new bus, and the voltage at the new bus will measure using KVL, and the current we will use KCL. So each section will have its own fault detection algorithms, and the fault location using each of the parameter of the line. Okay, for example, when the fault detection locate for this part 3 to the X, the new bus, then we have used the overhead line parameter in order to estimate the fault location in this line. Here is the overall process for wide area fault detection allocations. So normally for this project, we start with modeling the network using the ATP draw, and then we once we completed, and we will measure the all the signal will be gathered and recorded, and then we will use it for the algorithm that we have developed. Okay. But before that, we have to use the 5 row strategy in order to do the placement for the voltage and the current probe on the buses. Okay. All the fault detection and fault location algorithm formulations will be done in the MATLAB Simulink. Okay, it has to be done in this MATLAB Simulink. Here shows the fault detection and fault location block that we developed in the Simulink. So for example, here is a combined fault detection and fault location for all lines in 5 bus network. We have a 7 line here, and this is for 39 bus. We have the 34 lines. Okay. So this is the model and simulation of transmission network. So you use the ATP draw software. Okay, ATP draw software with started with the blank. Then we start modeling for 5 bus and also 39 bus. So for this simulation, we use sampling time for is a 1 times 10 power of negative 6 second, and the time for simulation is 0.5 seconds. And the location of measurement probes will depends on the PMU location strategy. Okay, so the line model that we use in this model is background type of symmetrical distributed parameters. Here are some figures taken from the simulations. So here is example of the current waveform during normal conditions, and also the example of current waveform during fault conditions. Okay, let's see the simulation result. So first, the result based on the wide area fault detections. So here is example, the positive sequence fault current flow into the fault points, and B, we have the fault detection signals. So from this figure, we can see that the fault started at 0.1, and then at time 0.1187, the fault has been detected. Okay. And for faults, all lines in 5 and 39 bus networks, we varied the fault types and also the fault locations and also the fault resistant. Fault types, we have unsymmetrical and symmetrical faults. And the fault has been set to occur at 0.1 seconds. So for 5 bus, we can see that all the fault has successfully detected, and the average fault detection times for fault initiation time is 0.01 second, or less than 1 cycle. Okay, and for the 39 bus, we found that all faults has been successfully detected, and the average fault detection times from fault initiation time is 0.021 second, or 1.268 cycle. Okay, this is the result for the wide area fault locations. So it's been done for 5 and 39 bus network. And in this simulation, we varied the fault types. We use symmetrical and unsymmetrical types of faults. And the distance of fault also we varied, and also the fault resistance we varied from 0 to 100. And this is the formula that we use to do the calculation for the errors. So for example, here 5 bars, it shows the accurate result. Okay, so the average error of fault location is 0.027%, or equal to 0.14 kilometers, which is less than 1 kilometers. And for 39 bars, we can see that the result quite good, and the average error of fault location is 0.826, or equal to 0.8 kilometers, which is less than 1 kilometers. Okay. So for the effect of the charging current on fault location estimations, we have tested for 3 different line lengths. So we have a short, medium, and also long line lengths. Here we compare the positive and negative sequence fault locations, and we can compare it using the error in kilometers. Okay, for example, for short line, and the average and maximum error for short lines are very small for both sequence fault locations, for positive and also negative fault location techniques. So for short line, both sequence fault location are not affected by charging currents. However, if we look on the long lines, the average and maximum error for positive fault location is higher compared to the negative sequence. So in this case, the negative sequence fault location still have small fault location error. Okay. So let's see the charging current that we measure during the single line to ground faults. So for the AG fault with the fixed of fault resistance 50 ohms, we have used it along line 1, 2, and with the increment of 10% from the total length. Okay, so here we can see that the positive sequence charging currents increase with the increase of the fault locations. And for the, this is for local, measured from the local, and for the positive sequence charging current measured from the remote, it decreased with the increase of the fault locations. Okay, and the total charging currents is the same for the all fault locations. Okay, and this high positive sequence charging current during the fault condition will influence the fault location accuracy for the positive sequence fault location technique. Okay, while for using the negative sequence fault location technique, we can see that less effect on the fault location accuracy, and it can be assumed that the charging current is insignificant to the effect on the fault location itself. So you can see that the current is small compared to this one, okay, positive sequence. Okay, general conclusion due to the effect of the charging currents. So the higher the line length, the higher the effect of charging current on the positive sequence fault location, especially for the single line to ground faults. And for the single line to ground fault, the positive sequence charging current which flow at the only faulted phase cannot be eliminated by positive sequence charging currents and other unfaulted phases. And you can see that from the positive sequence charging current, it will flow towards through the fault point as additional current to fault current during the fault conditions. This additional positive sequence charging current is not seen by the measurement instrument at the substation terminal. That's why it affects the fault location algorithms. While for the negative sequence charging current is very small compared with the positive sequence charging current. Thus, this is not affect the fault location algorithms. So here is the effect of fault figures for the fault resistant results. From the figure, we can see that the fault location algorithm is not affected by the fault resistant variations. Okay, it's very small. Now we looks on the effect of connected load variation on fault location estimation. Okay, here we have the figure for the load connected to PMU. The fault location for line 22, 23 with the PMU at bus 22 and 23. Okay, the single line to ground fault with 50 ohms fault resistance was simulated along line 22 and 23 for different load conditions. Okay, so from this we can see that the both positive and negative sequence fault location are not affected, okay, by the load variation that connected to PMU bus 23. Okay, so this is because the load is outside the boundary of line 22 and 23. So because the load was here, and this is the boundary of the measurements. And for this one is the positive sequence load currents shows it higher compared to the negative sequence load currents due to the balanced load conditions. In this, you can see that the negative sequence current are very small and can be neglected. For the second case, the load connected to the bus which are not installed to PMU. So here we have the fault location for line 1 to 39, okay, with PMU at bus 2 and bus 39, okay, bus 2 and bus 39. So the fault C to G type of faults is C to ground faults with 5 ohms fault resistance was simulated along the lines, line 1 to 39 for different load conditions. And we can see that from the result, the positive sequence fault location greatly affected by the load variations, load connected to the bus without the PMU bus. Okay, so this is because the load inside the boundary measurements here, the boundary measurements, the blue colors, okay, for line 139, and there will be a positive sequence load current flow through the load during the normal and the fault conditions. While for the negative sequence fault location algorithm is not affected by the load variation of the load connected to bus without PMU. This is because the load is in balance conditions. Thus, no or very small negative sequence load current exists during the normal and the fault conditions. So we can see that the negative sequence values error is less compared than the error for the positive sequence. So if we look on the currents, okay, we see that the positive sequence load currents are more than the negative sequence load currents due to the balance conditions. Okay, so this is positive, and there is a small value of negative sequence load currents exists due to these asymmetrical faults. So here is the result based on the hybrid non-homogeneous circuit. So for this, we test VG fault with the fault resistance of 10 ohm. We simulated along the circuit with 4 faults at overhead line section and 2 faults at the cable sections. Okay. From the result, we can see that the error is less using the proposed method compared than the one that without the proposed method. Okay, this is by using we assume that the line is homogeneous circuit. Okay, so general conclusion on the hybrid for non-homogeneous circuit. So both method successfully detected the fault section for all fault locations, and the proposed method has very accurate result compared with the methods which assume the circuit as homogeneous. And the proposed method use separate fault location algorithm for overhead lines and cable sections which have different distributed parameters. First, for a fault will be detected whether it occur at the overhead lines or cable section. Then the correct distributed parameter for the fault section will be used to estimate the fault locations. And the higher error of method which assume the circuit as homogeneous is because the method use the calculated distributed parameter which are not the same with the actual distributed parameter for the faulted sections. From this work, we have compared with at least 10 reference literatures, and we compare the types of measurements, the proposed type of placement, the average faulted line detections, and we can say that it's a par with the all other researchers. Okay, and some of the researchers, they didn't count the PMU placement strategy on their works because they assume that the measurements are available for the certain buses. And for the summary, the developed 5 rules of PMU placement have successfully determined the limited number and strategic location of the PMU. The developed algorithm produce accurate result of fault detection allocation for various fault conditions with different fault types, fault resistance, and also the fault locations. And the fault algorithm is not influenced by the line charging current, fault resistance, and also the connected load variations. The proposed algorithm, which use the sequence values, are much simpler compared with the algorithm which use the phase value. And by using the wide area fault detection algorithms, the maintenance crew will not have to go to the substation to extract the fault information from the relay, that they can use the WEMS techniques. And thus, the overall time, which includes the time to determine the actual fault line, locate the actual fault locations, and to do the repair and energize back the fault line, can be reduced. There is some recommendation from this work. For the next, we have to look the consideration of the untransposed transmission circuit, because in the line sometimes we have the transposed and also the untransposed transmission circuit, and we also have to consider the synchronization error when we do the calculation for fault location algorithms, because the sometimes we have miss communications that some data will not receive accurately. And also we have to consider the multiple fault occurrence at one time. And last but not least, we have to consider the FACTS device for this kind of work. Okay, I think that's all from me from the presentation. Thank you to all that watching this webinar. Okay, I give back to the MC.
So thank you, Dr. Rafi. That was a very interesting presentation, especially on fault location. And I believe uh, participants, viewers have a lot of questions. So you all can post the questions on the respective platform, whether it's YouTube or Facebook, and we will read these questions at the end of the second speaker session during the Q&A. So thanks again, Dr. Rafi. And
Okay, thank
now,
you.
thank you. So, and now I will introduce our second speaker for today, Dr. Dalila. So, Dr. Dalila Ahmad Said is an associate professor at School of Electrical Engineering, University of Technology Malaysia, UTM. She has been with the Center of Electrical Energy System, CEES, UTM, since the year 2009. She has 15 years of experience in teaching electrical power engineering courses and has been involved in power quality consultancy for over 10 years and served as an energy auditor for the commercial and industrial sectors. She is a senior member of the Institute of Electrical Electronic Engineer, SMIEE, Certified Energy Manager, registered with ASEAN Energy Management Scheme, registered graduate engineer with the Board of Engineers Malaysia, and also a graduate member of Institution of Engineers Malaysia and Professional Technologies with MBOD. Her principal area of interest is power quality and power system measurement and monitoring. Today, Dr. Dalila will deliver a presentation on her research area titled Power Quality, Introduction, Measurement, and Monitoring. Thank you. Dr. Dalila, the floor is yours.
Okay, Assalamualaikum and a very good morning. Thank you to Dr. Kandidra for your kind introductions. Thank you to the first speaker, Associate Prof. Dr. Rafi Azman, for very interesting sharing session. And thank you to all today participants. It is my pleasure to share my research experience on power quality, measurement, and monitoring. So, I will divide my session into 4 parts, starting with the introduction on power quality, followed by PQ measurement, monitoring, and data analysis, my research experience, and potential research collaboration, power quality, and Center of Electrical Energy System. Good. Okay, I start with the PQ analogy. So, graphical view is one of the useful indicator to help people investigate and identify the problem. Based on this, I will take the pointer. Okay, based on this electrocardiograph reading, from the graph, doctor will identify the condition of her or his patient. Okay, next, refer to this blood test. On the right side, you can see the different components have been measured. The result provide the score value, standard range, unit, and flag. And the red color of result with the flag indicate the reading are out of the range. Therefore, the question may arise here. Is the patient healthy? And what is the suitable solution? Only doctor can give a good advice to this patient. All this reading and data needs the measurement and testing device handled by an expert. And by having the knowledge on this area, the decision and suitable solution will be proposed. So, next, how this applies to power system. We can see in the left side show an example for the single phase system and the right side for the 3-phase system. As a general consumer, if we look at the waveform of the supply from the utility, can we identify the problem of the supply? As we know, the supply rated is 240 volts, and typically each cycle repeats at a frequency of 50 Hz. Clean or healthy power means that the supply AC current and waveform voltage are purely sinusoidal waveform. without any deviation either in voltage, current, or frequency. So, the next figure shows an example of the distorted waveform compared to the ideal supply. The dirty or unhealthy power is any deviation in the waveform in terms of either voltage, current, or frequency. Therefore, in order to know and investigate how healthy the power supply, the measurement equipment is required to monitor the system. The different pattern of waveform deviation can be classified as power quality problem. Next, we refer to the electrical power system. As a user, one of the key to understand power quality is to understand how electrical power arrives to our wall socket. Electrical power is derived from generation station that converts another form of energy to electricity. From the generator, the electricity is transmitted over long distance at high voltage through the transmission line. Power is distributed locally through the distribution system and local utilities, and the voltage at distribution system is reduced to the appropriate level and supplied to the customer. The power supplied to the customer by the utility will be either single-phase or three-phase power. So, after we understand the flow of electrical power from the generation to the consumption, we identify three parties that involve in power quality issue. First, utility or network operator or electricity supply. Second is the consumer, and third is device manufacturer. If there are power quality problem or issue arise, who should be responsible? Who we want to blame? Since this is not game to blame each other, then we need to study and understand the mutual among the three parties. Okay, refer to this figure. This figure shows the mutual responsibility sharing on power quality aspect among the utility, the consumer, and also the device manufacturer. From this view, as a utility, their focus to make sure the supply and good quality to their customer or keep electrical disturbance from affecting their equipment and their customer equipment. As a user, they require a good quality of supply, and at the same time, they need a standard to keep user create electrical disturbance from affecting the operation of equipment owned either by the utility, other end user, and themselves. Manufacturers need to be sensitive to produce electrical equipment that follow the standard and regulation. For example, immunity level follow IEEE 61000, 4-11, or 4-34, SEMI or 47, ITIC to keep their customer protected and satisfied. Next, we go to the definition of power quality. If we refer to the IEEE, power quality is defined by the IEEE as the concept of powering and grounding electronic equipment in a manner that is suitable to the operation of that equipment. Basically, that means what works for you and your equipment. Every system and many loads are different and respond differently to PQ issues. Power and equipment are suitable for each other also means that there must be compatible between electrical system and the equipment it powers. They should also be compatible between devices that share the electrical distribution space. Refer to the IEC. Okay, the term used by IEC is electromagnetic compatibility. So the electromagnetic compatibility defined as the ability of an equipment or system to function satisfactorily in its electromagnetic environment without introducing electromagnetic disturbance to anything in that environment. Or the best measure of power quality is the ability of electrical equipment to operate in a satisfactory manner, given proper care and maintenance, and without adversely affecting the operation or other electrical equipment connected to the system. In IEC, there are two sides of the EMC equation that divide by source equipment whose emission must be limited, and also the equipment that need to have sufficient immunity to this disturbance in its environment within which it operates. So refer back to IEEE. From the list, IEEE provides a comprehensive summary on the types and classes of the disturbances that can affect the electrical power, which can be simplified by dividing them into 7 types of disturbance, starting with the transient, short duration variation, long duration variation, voltage unbalance, waveform distortion, voltage fluctuation, and frequency variation, where the first 3 types we can categorize as instantaneous and the remaining 4 as the steady state. So the next table will show the detail of the event. If we can see, for this classification is based on the length of time, magnitude, and also frequency of the occurrence. Under each type of disturbance, there are another type of event and problem. For example, we can see voltage sags is located under short duration variation, and harmonic under waveform distortion. Okay. And from this graph, we can see the classification of the instantaneous part in the graph, where the event occur for the less than half cycle is we consider as a transient. So for the event starting from half cycle to 1 minute, we can consider as a voltage sag if the magnitude is between 10 to 90%, and voltage swell if the magnitude is above 110%. And for the event occur more than 1 minute, we can consider the sustained interruption under voltage or over voltage that have been classified under long duration variation. However, not all the event or deviation may impact the operation of the machine or equipment. So, from the most power quality problem, I select 2 most common types in the power system, which are the voltage sags and harmonics. Okay. On the left side is voltage sag. Actually, voltage sag is a decrease of the normal voltage level between 10 to and 90% of the nominal voltage at the power frequency for a duration of half cycle to 1 minute. And the event are due to the fault on the transmission and distribution network, fault or the fault in a customer installation or a connection of heavy load and startup of large motor. The impact of this problem may cause the malfunction of information technology equipment, for example, microprocessor-based control system, and that may lead to a process stoppage. The second problem is, on the right side, is the harmonic. Harmonic, if we can see, voltage or current waveform assume non-sinusoidal shape. They have distorted. The waveform is correspond to the sum of different sine wave with different magnitude and phase, having frequency that are multiple of the power system frequency. And the problem caused by non-linear load connected to the system. The impact increased probability in occurrence of resonant, neutral overload in the 3-phase system, and overheating in the cable or transformer. So, based on the problem, why should we care or concern about the power quality? There are several factors, and why should we care? For example, at industry, each time if the voltage spike occur and they impact the industry or stop the machine, it may cause a failure on the equipment or the equipment malfunction. It will interrupt the production and also the business loss profit on the product that is not manufactured and sold. Interruption can damage a partially complete product, causing the material to be rerun or scrapped, and electronic card fail among impact arising from harmonics, condensers within the interference filter circuit board at card entrance may withdraw excessive current and explode due to harmonics, and they may lead to the poor production and also poor quality of production, poor operational efficiency. Harmonic in the transformer also will increase the heat and insulation problem with losses. Overheating also is one of the negative results of harmonic source skin effect on conductors. So, what we need to do? So, based on the problem that highlighted before, PQ measurement and monitoring must be done to solve the power quality problem. Monitoring may be as simple as a person indicate power quality symptom. For example, we can see the light flickering. So we can say that maybe there are a voltage fluctuation because the light flickering. But if it's the best if we done with today modern power quality meter, which comply with IEEE 61004-30 Class A measurement standard. So next we go to the definition of what is power quality monitoring. Actually, the power quality monitoring is the process we collect the data, and after we collect the data, transport the data to somewhere it will be useful, and then we convert the data into decision-making information. It also helps to identify the power quality problems, minimize the losses in the production, and increase the plant productivity. However, to doing so, it requires an investment in equipment, or we will invest for the consultation, time and education, and to gain more knowledge about the power quality. Usually, when we want to do a measurement or monitoring, when is the suitable time to monitor? There are 4 suggestions here where we can start to do before any expansion or installation of the equipment, or after the problem occur, or we suspect they have a problem, for the purpose of formulation of guidelines, and as the utility or electrical supply and some industry and commercial, they will monitor power quality continuously. However, the most request is after the problem occurrence and suspect. Here is the suggestion where we want to measure. Okay, so based on this problem reported, another important aspect to monitor location when characterizing specific power quality problem is to locate the monitor close as possible to the equipment affected by the power quality variation. If there are suspected equipment, we need to install the PQ recorder close to that sensitive equipment. If the problem occurs at the entire facility, the suitable location is close to the source or at the PCC or at secondary side of the transformer. If we suspected all equipment connected to the branch exhibit the problem, we can put it at major node or branches. So here I will share some tips before we start the logging and monitoring. Of course, in order to handle the measurement or installation, we need to follow the regulation and guidelines. Okay, sis, this is a tip before we start the monitoring. Make sure we check all the connection. The tips also may be applied if we use the different type equipment. First, we check the connection at the current claim. Usually the current claim provide an arrow that indicates the direction from the source to the load. That this, we need to carefully check the direction on the current claim. And the second one is we can check the scope, function, and also if we have the three-phase system, we should see something like this, that all the three-phase is out about 120 degree. And also we can check the reading on the meter. And another part, we can check if you carefully observe this type connection, you can see what is the error in this type of connection. And this is also the important part that we need to check before you want to leave your monitoring for about a week or a month or a year. But even we have for the long duration, we need to check the data frequently. So this is some tip before we start logging and monitor. So from the above discussion, I can summarize and conclude the process of measurement and monitoring power quality. A measurement of power quality requires the use of proper instrument to suit this application. The user of the instrument must be well trained in the use and care of the instrument. Starting with the measurement process, we need to consider the safety measure, where we want to install the device, what the type of disturbances that we need to capture, because we want to know the duration. If this is only a steady state, okay, it is enough to install about 1 week for the 10-minute interval. If this is the instantaneous event such as voltage sag, maybe we need to install about a month or a year, depends on the situation. And of course, the verification and checking after the installation. Usually for the site visit, during the site visit, we can see and check what is the suitable size of current clamp, or do we need to bring an extension wire during the installation. And during the site visit also, we will share the single line diagram, and of course, the person who want to handle the monitoring device should study the manual of and have experts how to use the PQ analyzer. For the data analysis, after we have transferred the data to the computer, usually most of the measurement device provide with the simulation, so with the software provided that we can take the data. Either we want to plot the trending, compare with the limit, we correlate the event with the other event, and with the enough data, we can propose a suitable mitigation. And for the mitigation, usually we can consider what is the installation for the mitigation and the payback period. So next, we want to go to data analysis. Analysis may be an engineer evaluating meter data, or even performing computer simulation, or today maybe artificial intelligence software looking at waveform and making a determination. Even every problem can be solved with the right clues, but sometimes clues lead you down to wrong path. So therefore, proper analysis need to be performed. So I start with an example of data analysis for voltage sags. So in this section, I will cover voltage sags, harmonics, and also other PQ problems. So if we refer to this data, okay, this data refer to the Energy Commission Annual Report 2019. So in 2019, there are about 805 voltage sag occurrence recorded in Peninsula Malaysia. This total number contribute from each state as shown in the below bar chart and record from the 173 recorded in the MB system. From the graph, we can see Selangor and Perak contribute the highest number of occurrence, which are 140 and 135 events respectively. And the pie chart show the number of recorded at each state. Okay. Of these 805 sag occurrence, about 77 were categorized as an affected region, meaning that the voltage set did not affect the customer operation in their equipment, complies with the MSIEC 61004-34 standard. And the remaining 22% were categorized as affected region, where the voltage set caused the equipment to stop operating. The 805 set occurrence affected about 292 customers. Of this also, we can say that about 77.1% were above the immunity level and the remaining were classified as below immunity level. So next, we see what is the factor contribute to this event. Okay, from this, this is the cause of voltage sags at transmission line, and we can see the highest contributions and the primary cause of voltage sags on transmission line was lightning strike, followed by the damage, overhead 16%, and they have unknown cause about 11%. That's the cause of the voltage sag at the transmission line. However, at the distribution line or distribution system, we can see most voltage sags were due to the unknown causes. Other causes such as damaged cable, cable fault, damage on cable and cable joint, transient fault, and damage of the headline inductor. And usually for the highest unknown cause, usually refer to a transient or internal fault at the customer side. So based on the event, in order to investigate the impact, we can check and we can refer to the immunity level provided, such as in the CBMA, ITIC, IEC, and SEMI F47. So next we refer to this curve. Okay, this is the Computer Business Equipment Manufacturer Association curve, published in IEEE standard 446. Is intended to illustrate the suggested computer susceptibility lines. And the red lines indicate the CBMA curve, and the black lines indicate the ITIC curve. Okay, the curve, the CBMA curve was derived by CBMA Association in 1970. To describe, actually, the purpose of this curve is to describe the tolerance of mainframe computer business equipment to the magnitude and duration, of the voltage variation of the power system, and to point out way in which the system reliability could be provided for the electronic equipment. In 2000, CBMA curve was renamed as ITIC curve, where ITIC curve is published by Information Technology Industry Council, formerly known as CBMA. This could provide an AC voltage boundary that most information technology equipment can tolerate or ride through without experiencing unexpected shutdown or malfunction. Information technology equipment could include single-phase computer, printer, and scanner. Both curves have three regions, where the first region we can mention as the no interruption or in function region. So means that if you have an event in this region, equipment should operate satisfactorily. The second region is the prohibited region. So for this prohibited region, event such as soil may damage and might result for IT equipment. And the third region that we can classify as no damage region, if an event such as voltage sags occur, the equipment may malfunction. Another standard related to this immunity level of voltage sag is SEMI F47 and IEC 61000-4-11 and 4-34. So we can see the difference between these two standards. For -11 is for the electrical equipment less than 16 M, and for the 4-34 is for the electrical equipment more than 16 M. So these both standards, or the SEMI F47 is an industrial standard for voltage sag immunity. It states that industrial equipment must tolerate voltage sag and the AC main supply to specific depth and duration, if you can see the curve. It is useful standard. Many other industries use it, either formally or informally. And for the IEC, define the immunity, test method and range of preferred test level for electrical and electronic equipment connected to low voltage power supply network for voltage dip, short interruption, and voltage variation. And the standard have different in test level and also the duration. Both standard have only two regions. Different with the previous slide, we can see ITIC and CBMA, we have three regions. However, for the SEMI and MS-IEC 61000 4-11 or 4-34, we have only two regions, where the above region as the unaffected region and the area below the curve is the misoperation or malfunction region. So next, how this apply? How we apply? I will show an example of the data plot on the graph of the standard. So from this graph, okay, I explain again detail on this standard. We have the voltage sag magnitude, which is the percent of the nominal value, versus the duration of voltage sag in second. The black color in this graph is the MS-IEC 61000 4-34. And the remaining color is EUT. EUT is stand for equipment under test. So when we have performed the immunity test for the different type of equipment and we plot on the graph, we can see that equipment under test that comply with the standard is only EUT1 and EUT2. However, EUT 3 and 4 violate the standard as the curve above. They have a curve that's more than this standard. Okay, so both EUT 3 and 4 not comply with the standard. Next, if we have an event, for example, if we have an event of voltage sags that we have captured, the magnitude and also the duration, and we can try to correlate the event data in the plot graph. So we can see the location of event A, event B, and also event C. It can see that event A is at the upper region and may not impact any EUT. So all the EUT will function. However, for event B, it's located below EUT red color, which is EUT3, and also EUT4. Means that it may cause both equipment to malfunction. And event C, it's located at the upper region of EUT1 and may cause EUT2, 3, and 4 to malfunction. Okay, after we have found the problem and we see the impact of the event, as a user, of course, we want to know from where the source comes from, either from your internal or from external. So we refer to this graph. This graph we will obtain through the monitoring process. When you capture the event, you can see, if you refer to this graph, the graph show the three-phase voltage and also the three-phase current. For external fault, if the voltage drop, the current also drop. We can observe this data from the recorder, and the concept is during a fault, the load is considered constant. We consider the load constant, means that we apply the basics Ohm law, V equal to IR. The load is considered constant, and the occurrence of voltage side can be you analyze using the Ohm's law. When the voltage from the supply drop, the current tend to drop because the energy is not supplied to the load, but divert to the fault that occur outside of the premise. This is that you can observe. This is due to the external factor. And for the internal fault, from the concept of power P equal to VI, and V and I is the voltage and current respectively. During the startup of a large load or motor, the incoming power is considered constant. The current will be increased as it has to supply the large load, which will make the voltage tend to decrease. Means that when the voltage decrease, you can see the current increase, that we can suspect it due to the internal fault. So next we go to the second part of data analysis, which is harmonics. Harmonics, we can represent the data either in frequency or the frequency domain or time domain. Usually in the time domain known as the waveform, harmonic waveform, and in the frequency domain known as the harmonic spectrum. From the spectrum, actually, we can see detailed contribution of each harmonic order, and the harmonic number indicate the harmonic frequency. The first harmonic is the fundamental frequency, which such as 50 Hertz. The second harmonic is the component with frequency 2 times the fundamental, and so on. In most areas, the voltage found on transmission system typically has much less than 1% distortion. However, the distortion increase close to the load. Usually, end user sector suffer more from harmonic problem than does the utility sector. Actually, harmonic problem is not a new phenomena on power system, as we can consider harmonic as a new normal in power system. And the parameter mostly used to analyze harmonic, we can use either individual harmonic distortion, we can calculate for both current and voltage, and also the total harmonic distortion. The individual harmonic distortion means that it indicates the contribution each of harmonic frequency to the distorted waveform, and the total harmonic distortion indicate and describe the net deviation due to all the harmonics. And another important indices when dealing with the harmonic is true power factor. True power factor is the power factor that consider the harmonics. And displacement power factor is the power factor without harmonic effect, where we consider from the cos theta or P over S that we calculate. That's what we call the displacement power factor. And the relation between the displacement and true power factor, actually how you want to calculate the true power factor. The true power factor can be calculated by using the displacement power factor multiplied with the distortion factor. And how we want to get the distortion factor? We can use both the contribution of total harmonic distortion from current and total harmonic distortion from voltage to calculate the distortion factor. And we will get the value of true power factor. So this is an example of harmonic data, both THD value and THDI for current and THDB for voltage, and the impact to the true power factor. The blue color indicate the true power factor, and the purple color give the displacement. We can see the different value. And the line here is the limit set by TMB, which is 0.85. So next we go to the analysis, the next analysis in harmonics. So by considering the harmonic data for the three-phase system, we will consider how to analyze the impact of this individual harmonic to the increase of loss for the transformer. So, but before that, I just want to show how we want to check this harmonic data with the limit. So let's say we take the limit standard, for example, IEC 61000 3-4. This is limit of emission of harmonic current in low voltage power supply for equipment with rated current greater than 16 amp per phase. So from this data, you can see the gray color that I plot here indicate the limit, and we can see the third, 9th, 11th, and also the 17th order harmonic has exceeded the limit. This excessive will increase heating and also will increase the losses in, especially in the power system. From the data also, in order to study the impact of harmonic on transformer, we consider what we call the harmonic loss factor. This harmonic loss factor was identified by considering the contribution of all individual harmonic data. IEEE C57110 have developed harmonic loss factor as a method to determine the summation of harmonic order. This factor can be used as a multiplier on the winding eddy current losses and also other stray losses. Both factors can be normalized to either fundamental current or the RMS current. And we can see the formulation for the burst factor. So by using this formulation and also by considering all the harmonic losses due at the transformer, for the load losses. So there are two different case analysis have been considered. The first one of the case, we consider the different per unit loading for the different of total harmonic distortion for current. So based on the analysis, we can calculate the percentage loss increase due to this harmonic. From the result, losses with and without harmonic also can be classified clearly. And the case 2 here, an example also for the different harmonic distortion with the same per unit loading. There are two cases here. That the first one we can consider as the high harmonic and the second one as the medium harmonic. So from this analysis, the per unit life of transformer can be determined by referring to the Arrhenius reaction rate theory as mentioned in IEEE standard C57.91. Figures show that the transformer life versus the per unit loading. Okay, and for the first, we can consider at low, medium, and also high THD value. Refer to this figure, we can see that for the low harmonic distortion, the transformer will maintain its normal life until 1.15 per unit for low THD. And for the high THD, the transformer will maintain its normal life until 0.63 per unit load only. So we can see the impact of harmonics for the lifetime of the transformer. And harmonic distortion also have a negative effect on the transformer efficiency in addition to other losses. The loss in the distribution transformer affect the price of electricity as well as system losses. The effect on losses have been studied in terms of the cost with respect to the linear and non-linear load condition. And the expected value of economic damage is divided into the operating cost and aging cost, and the total consideration of increased cost of losses and aging costs with effect of harmonic. So we can have categorized the different sector and for the different category of harmonics. So based on the data obtained through the 5-site monitoring, we can estimate the losses of transformer, and we calculate the increased cost of losses due to harmonics that contribute about 5 million for industry, 1.6 million for the commercial, and around 900,000 for residential area. Actually, residential area is not for the individual site. It is take the data from the substation at the residential area. Okay, so the next analysis is power quality performance indicator. So this indicator, power quality indicator, designed purposely to identify the performance level of power quality at the substation. So starting with the data collection, analysis, coding, and come up with this appearance that to indicate the substation's performance. And the percentile method is used to determine the individual power quality characteristic. The compatibility level for the power quality problem is defined in terms of 95% percentile, being lower than a certain value. It can be defined for all continuous phenomena such as flicker, voltage variation, and the total harmonic distortion. This indicator is based on the color coding, which green, yellow, or red. And green indicate a good quality, yellow indicate action need, and red refer to the poor quality. I show an example of the indicator. So this is an example of output run from the selected substation where all the parameter in green except one PLT value indicate the warning. This is yellow color. Of course, in order to develop this indicator, it follow all the requirement standard so that the facilities department will get the exact information from this indicator. And therefore, this indicator will help user for early warning before any equipment damage that may cause a huge cost of replacement and to ensure the good performance of every substation that continuously responsible to give sufficient supply to the customer according to their demand. And just here I list some standard regarding to the measurement where IEEE must refer to IEEE 5519 and IEC standard is referred to 61000-4. Each provides a detail about the specification for monitoring harmonic level. So the third part in my presentations just to share my experience in power quality research. So starting refer to the timeline in the table, I can summarize my experience based on the timeline. Actually, my first involvement in power quality is starting with my Master by Thought course project. This is my first experience involving with the power quality measurement. I done this project under the supervision of Professor IR Dr. Abdullah Suhaimi Muhammad Zaid, and this project present with the harmonic measurement simulation using SKM power tools and install the filter using the simulation to improve the harmonic distortion. And the specific case study have been conducted at Faculty of Electrical Engineering, UTM. So next, the second part of my involvement, I continue my PhD also in the same area, focus on harmonic impact on distribution transformer. The project, I start my PhD research on 2007, supervised by well-known professor in power engineering, Professor Dr. Khalid Muhammad Noor, and Associate Prof. IR Mat Shah Majid. And this research also involved power quality measurement and analysis for the purpose of estimation and accurate transformer losses due to harmonic problem. And the result was validated using the measured data. And the achievement from this research, I just want to highlight the research interest in harmonic impact on distribution system, where it treats the reach as about 15K. Therefore, it have a more opportunity to study on the impact, especially now we can consider interharmonics, and at the same time in the analysis we can also consider the impact of both total harmonic distortion, voltage and current. So the next, the project related, my research project that related to the power quality. So this table show the list of the grant that awarded to me to conduct the research, mostly focused on the power quality. It's starting with the experimental works, where an experimental study on harmonic impact step-down transformer in end-user equipment. And the latest one that I secure is with the title of Energy Management and Power Quality Monitoring Framework for Smart Building using IoT. So next, the refer back to the timeline is related to the postgraduate study. This project supervision, I supervised the project related to power quality harmonic modeling and analysis. Most of the title related to the power quality, and up to date I have 4 graduated PhD and 2 graduated masters. So next is the selected consultation project related to the power quality and energy audit. And this is the list of the project. The major power quality works that are involved in is the power quality baseline study in Peninsula Malaysia, because the project gives me a lot of exposure to the power quality scenario in Peninsula Malaysia. So this in early 2010, the Energy Commission of Malaysia have commissioned a power quality baseline study for Peninsula Malaysia consultation project, and this project was awarded to Global Technology Innovation and Management UTM Sdn Bhd, the consulting arm of University Technology Malaysia. That expertise that undertake the project is from the Center of Electrical Energy System and one of the research center in the UTM. Okay, so the projects also involve the PQ monitoring at about 50 sites and 500 site PQ logging, and there are 2 industry collaborators involved in the project, Data Rembliance in Bhd and also Advanced Power Solution. So this is the we have developed the online power quality monitoring system, and it has successfully collected the data in a real time in Peninsula Malaysia. So for the installation, Data Rembliance supply the competent person and also the transportation for the PQ logger installation. And also the safety is the top priority, especially when we're handling the electrical installation. And also we need to follow all the provided guideline and regulation. The figures show the data logger monitoring personnel. And for the database, with the collaboration with Advanced Power Solution, we developed the PQ database, the detail. And of course, during the project, they will need to organize 2 workshops and also 4 seminar. The workshop for the stakeholder, Energy Commission, and also the relevant parties. The objective is to gather input, feedback, suggestion, and consensus on the finding and outcome from the project. And also 4 seminar conducted by the consultant to Energy Commission staff. And the objective of the seminar, we want to introduce the basic knowledge of power quality, introduce and discuss the power quality monitoring system, discuss about the standards and so on, and also focus on the interactive graphical open data software, that power quality software developed by the consultant team during. And another related project and research activity with the power quality again that are involved is in 2008, during the energy audit at Pro2, they also request on power quality audit, and another research project involved on installation power quality at Alpha Industry and also at RTM. And in 2009, I focused on PQ logging at UTM substation, where from here I have developed the PQ indicator. And also we have another PQ data logging at pump house. So besides research and consultation works, PQ syllabus at university students need to comply, or the learning outcome is have an ability to handle the measurement device. So student exposed to handle all the power quality device by performing measurement in the lab. However, if for the small size of group, I will bring the student to the site. Next, as a summary, PQ awareness are important, especially for the utilities or facilities engineer. They need to know because they need to make their system in a good condition and have a good supply. So, and they will identify if any problem occur in the system. The correct measurement and monitoring data important to identify the actual problem before any mitigation action have been taken. So to make sure that we have select the proper and the right solution to the problem. And the business risk caused by power quality problem cannot be taken lightly because it can severely cause financial losses to the industry that and also the commercial sector. So the last two slides is just to highlight about the potential research collaboration. We have an expert in our center. Actually, this CIS established in 2009 with the first director, Professor Dr. Khalid Muhammad Noor, from 2009 to 2012 after retired. The second director is Professor IR Dr. Muhammad Yusri Hassan, and the current director is Associate Prof. IR Dr. Muhammad Fawzi Abdullah, and I'm the deputy director. The research area in our center, we have energy efficiency and management, electrical power quality, renewable energy, power system analysis, smart grid application, and the related electric market. We also provide a consultation, training, and community surveys. And here also I can show an expert from our center, the research fellow, associate research fellows, and also the staff. Okay, I think that's all from me. Thank you. This is the reference. And if you interested to have a collaboration with us, we can contact our center. Thank you.
All right. Okay. Thank you, Dr. Dalila. So I think that was a very interesting presentation, especially on power quality monitoring, the relevant standards, and so on. So, so that comes to the end of our second session, the second speaker. So for now, I would like to start our Q&A session. All right, so with both Dr. Dalila and Dr. Rafi, right? So participant can post your questions on the comment box in Facebook or YouTube, and we will read the question. But just to get the session started, perhaps one question to Dr. Rafi. So Dr. Rafi, what is your comment about feature extraction? And do you think feature extraction is important for fault location or fault detection?
Yeah, I think from my opinion, based on these feature iterations, you can get lots more information related to the signal that you recorded, for example. So from this signal, you can extract many data from it. For example, you can get the voltage, the currents, the amplitude, the frequency, and from this feature iteration also you can extend to another kind of signal. For example, you use DWT or CWT. So then from there, you can use the information to develop different kind of fault location algorithm. Maybe you can use other artificial intelligence techniques in your formulation, for example. Sure, using feature extraction is good in futures. Dr. Kanidra, I didn't hear your voice.
Oh, thanks. I think we would go for questions from the participants. All right. So the first question is actually from Dr. Jasrul. So Dr. Rafi, for fault detection, why do we use positive sequence value during calculating the fault current and negative sequence value for calculating the bus voltage value?
Okay, thank you very much, Dr. Jasrul Jamian. If I can answer this question. Okay, for the first detection method, use a positive sequence value because it only wants to differentiate between the normal and fault conditions. If a fault occur, the total fault current will be very high compared with the summation of pre-fault local and remote currents. So using the positive sequence is sufficient because to detect. And for the second detection method, measure bus voltage using negative sequence because if we use KVL, there will be a load and charging effect from the adjacent line or buses that we have just showed before, okay, on the positive sequence. So from the result, we have proven that the negative sequence has a very small effect of the charging currents and the loads. So when using the negative sequence, the magnitude voltage that we calculate is more accurate than using the positive sequence. Okay, so if we don't use the second detection method, all lines that share the same measurement source will be detected as the faulted lines. So that's why we use the second detection methods. So there is a security on that kind of issue.
All right. Okay. Thank you. Right. Perhaps we can go to the next question. Okay. Question from Prof. Hazli. Dr. Rafi, what is your comment about the accuracy of the proposed method, considering the potential inaccuracy of wide area measurement system and some measurement is estimated using KCL and KVL?
Okay, thank you, Prof. Hazli. I like also to thank him because he personally invited me to present in this webinar. Okay, I think, of course, there will be an effect with the wide area measurements system if the input is not accurate. Okay, so in this work, we consider there is no communication error and we assume there is no synchronization problems. Okay, so if we follow the actual WAMs, we have to measure the latency, okay, the delay of the measurement from PMU location to the central locations. And in order to rectify it, we have to compensate the latency problems. Okay. Of course, in the real measurement, there will it will be not 100% the same measurement from the PMU and the measurement using KCL and KPL. That is why we propose to use the negative sequence for location and cannot use the number of PMUs that are too small. So we just need to optimize the numbers of PMU. So inshallah, maybe in future we can pick up this problem for using unsynchronized measurement when there is a signal loss. I hope I
Okay.
can answer.
Thanks. Thank you, Dr. Rafi. We could go to the next question. This question is to Dr. Dalila. What is the difference between voltage sag and voltage dip?
Okay, thank you, Ms. Hamizah Ismail. Actually, the voltage sag and voltage dip is the same term using. Voltage sag use US English or US used by US, or voltage dip used by the British English or UK. It's same, a short duration in RMS between the 10 to 30% of the nominal voltage from half cycle to 1 minute. That's why when you find the document published by US, most of them use voltage sag. However, for the document published by British, it will use the dips. Actually, it refers to the same thing. In this commission, we use the term of voltage sags.
Okay. Thank you.
Okay.
The next question, please. From Prof. Hazli. Dr. Dalila, from your experience, what is the best mitigation technique or equipment for harmonic problem at customer side?
Okay, actually, thank you, Prof. Hazli, for the questions. Okay, usually in order to mitigate harmonics, most of the industrial, they choose an active filter. Even active filter has the expensive cost compared to the passive filter because it will correlate and also at the same time avoid the resonant problem in the system. But it also need to refer and to investigate the detail. I cannot say this is the best, but it also need to depend on what the cause of the problem. At this situation, they choose the inductive filter. Okay, thank you.
Thank you. The next question from Dr. Farid. So Dr. Rafi, very interesting sharing session. I just wonder why does your technique does not consider the zero sequence component?
Okay, thank you, Dr. Farid. One of the things that we thinking at the first when we run this project, we try to not consider the zero sequence components since we know that we want to eliminate the effect of the fault resistance on our calculations. That is one of the reason why we didn't choose the zero sequence components. Okay, so and also you can see that when there is a effect on the charging currents when there is a single line to ground happen to the line, so that will be also affect on the zero sequence component as well.
Okay, thank you, Dr. Rafi. The next question, please. This is for Dr. Dalila from Dr. Farid. From your opinion, do we need to develop PQ standards for maritime or shipping system?
Okay, thank you, Dr. Farid, for the questions. Okay, in my opinion, the standard have been developed according to the specific voltage and range of the currents. So, regarding to the standard for maritime or shipping systems, it may have a suitable standard that we can refer. For example, if you have an equipment or device for that specific, we need to make sure that that your equipment will follow the certain standard either provided by IEEE, IEC, or also engineering recommendation as used mostly in TMB. So maybe if they are required a specific, yes, I think also we can use and refer to the specific standard for the system.
Right.
Okay, if I answer your question, Farid.
Okay, thank you, Dr. Dalila. And the last question from me, with the introduction of electrical vehicle, do you foresee that more power qualities issues will arise?
Okay, so when the introduction of that electric power vehicle that connected to the system, and at the same time we also need to concern about the impact of power quality. So as long as we concerned about the problem will occur, we need to take an immediate action before the contribution of such as distortion come to the system.
Right. So thank you, Dr. Dalila. And I think those are the questions for this webinar session. So thank you to both speakers, Dr. Dalila and Dr. Rafi. For the participants, if you wish to have further questions or perhaps further research collaboration, you can contact both Dr. Dalila and Dr. Rafi based on your research interest. And with that being said, please join us for the next event, which will be next week. Oh, I think before we end the session, there is 2 more questions that has come in. Dr. Dalila, this is from Che Agong. Among the line-to-line voltage seg and line-to-neutral voltage seg, due to transmission line fault, which one gives the most effect to the industrial customer load tripping?
Okay, it depends. When we are considered for the type of fault, actually to give impact to industrial equipment, it depends to that industrial immunity level. If the industrial follow all the device and equipment follow the standard, they may not get impact due to the event. But in detail, when the question asks for different type of fault, that I have the information from the data just now is the total number of faults that caused by the lightning strike. For example, for the lightning strike, it may cause any type of fault. So in order to investigate detail the impact to industry, so the important is, it depends to the industry. The specific data on that, I didn't have that data, that this is the lightning strike due to what type of and cause what type of fault. But what I can say, if we are referred just now from my immunity level lines and also the plotted graph, we can see if your equipment is enough and comply with the standard, it may cause your equipment to function without any interruption if the fault occur in the system. Thank you.
Okay, thank you, Dr. Dalila. We have one more question. I believe this is the last question. Salam, Dr. Dalila from Encik Saiful. Is it possible that there are multiple disturbances in Malaysia? Do you have any data, or what are the common multiple disturbances in Malaysia?
Okay, thank you for the questions. I'm very clear what's the meaning of multiple disturbances. Maybe the meaning is we get more fault quality occur at the same time. Yes, it's correct. Of course, in a research area also, we are studying the impact at the same time, the impact of distortion on waveform, and also we have a voltage sag occur in the system. So it may occur in the system, even you have a active filter in your industry. It doesn't mean you may impact due to other problems such as voltage sags.
Right. Okay. So thank you, Dr. Dalila. And again, I think those are the questions. So again, thank you to both speakers and also to the participants. You can always reach both speakers to their respective contact details, which was displayed earlier in the presentation session. And with that being said, we would welcome you for the next session, which will be the last of this engineering research discourse series. So thank you to all participants and thank you to both speakers. Right, thank you.
Okay, thank
Okay,
you
thank
all.
you.